somewhere on our planet lies one of nature's most puzzling creations, a phenomenon scientists are still working to understand. If it vanished today, no human lifetime would be long enough to see it return. Nature would need millions of years to create it again. And strangest of all, its story may begin with something as ordinary as a shark's tooth. Picture a place where morning never comes. No ray of sunlight reaches here. The pressure is immense, enough to destroy equipment not specifically engineered for the deep ocean. The water hovers just above freezing, and the surface lies several kilometers overhead. Millions of years ago, a shark's tooth may have settled onto the seabed and become the nucleus of a process far too slow for the human eye to witness. Atom by atom, layer by layer, minerals begin to accumulate around that tiny fragment. In some nodules, even a few millimeters of growth may take 1,000,000 years. And then comes the true scale of what lies below. Within the Cook Islands' exclusive economic zone, current official estimates suggest that the seabed may hold around 6.7 billion metric tons of wet polymetallic nodules. So, what exactly are they? And why does nature need 1,000,000 years just to add a few millimeters? They are polymetallic nodules, dark, rounded mineral formations, often compared in shape and size to potatoes, scattered across the abyssal plains of the ocean floor. A nodule grows gradually, layer upon layer, around a small nucleus. That nucleus might be a fragment of rock, a piece of shell, or a shark's tooth. Metals supplied by seawater, and, in some regions, by pore water within the sediment, accumulate slowly around the nucleus. Manganese and iron form much of the mineral structure, alongside smaller concentrations of nickel, cobalt, and copper. Cut a nodule open, and you may find concentric layers, not unlike the growth rings of a tree. But here, the time scale is entirely different. A nodule small enough to fit in the palm of your hand may have begun forming long before our own species appeared. And it is not simply an inert object resting in an empty landscape. Across the soft sediment of the abyssal seabed, a nodule provides a rare patch of hard surface. Sponges, anemones, and microorganisms can attach themselves to it. In a world dominated by mud and permanent darkness, it becomes a small island of life. In the summer of 2026, 2 scientific expeditions are exploring little-known regions of the Pacific. NOAA ship Okeanos Explorer is working in the deep waters of the Cook Islands, while E/V Nautilus is surveying abyssal habitats and ancient seafloor around the Mariana Islands, including areas east of the Mariana Trench. Their remotely operated vehicles explore depths extending to nearly 6,000 meters, transmitting live images and scientific data through telepresence systems. Every dive is a journey into the unknown. And remarkably, life does not disappear at these depths. It simply takes different forms. The scale of what remains undiscovered is not confined to these 2 expeditions. In May 2026, the International Ocean Census Program announced 1,121 newly identified marine species, a 54% increase over the usual annual rate of species description. Among them was a new species of deep-sea ghost shark, a chimera related to sharks and rays, along with newly identified corals, crabs, shrimps, sea urchins, and anemones. During its 2026 Mariana Islands expedition, Nautilus has recorded rare purple acorn worms, deep-sea hydromedusae, and fishes adapted to extreme depth, across areas containing some of the oldest seafloor in the Pacific, and among the oldest on Earth. But the deeper question goes beyond any list of newly discovered species. At Earth's surface, Most ecosystems ultimately depend on energy from the sun. Plants and other photosynthetic organisms capture light, and that energy passes through the food web. Several kilometers down, there is no sunlight to use. Many deep-sea organisms depend on marine snow, the slow fall of planktonic remains, and other organic material from the waters above. Elsewhere in the deep ocean, however, some ecosystems work in an entirely different way. Seawater enters cracks in Earth's crust, becomes heated, and returns through hydrothermal vents carrying dissolved minerals and chemicals. Around these vents live microorganisms that obtain energy not from sunlight, but from chemical reactions, a process known as chemosynthesis. The discovery of these ecosystems changed more than oceanography. It changed our understanding of where life might be able to exist. Because if organisms can survive without sunlight on the floor of Earth's ocean, could something similar be possible on another world? Our solar system contains at least 2 worlds where vast oceans are believed to lie beneath shells of ice. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Europa is slightly smaller than our own moon. Its surface is solid ice, crossed by long fractures and disrupted regions. No human has ever set foot there, and no spacecraft has landed on its surface. But NASA's Galileo spacecraft made 12 close flybys of Europa and measured disturbances in the magnetic environment surrounding the moon. The leading explanation is that an electrically conductive fluid lies beneath the ice, most likely a global ocean of salty water. Enceladus is far smaller than Europa. Yet, this modest ice world has produced some of the most remarkable discoveries in the history of solar system exploration. From fractures near its south pole, plumes of water vapor and ice particles erupt into space. NASA's Cassini spacecraft flew repeatedly through this material and sampled its gas and ice grains. Scientists detected water, salts, carbon dioxide, methane, silica, and a variety of organic compounds. Together, the evidence points to a global ocean beneath Enceladus's icy shell, an ocean whose water interacts with a warm, rocky seabed, where hydrothermal processes may be taking place. None of this proves that life exists on Enceladus, but it does show that environments once considered utterly incompatible with life may contain several of the conditions habitability requires: liquid water, essential chemical elements, and sources of energy. This is why Earth's own ocean matters so much to space science. Its hydrothermal systems show how water can interact with heated rock. Its microorganisms demonstrate how life can obtain energy in permanent darkness, without a single ray of sunlight. To study Europa, NASA has sent an uncrewed spacecraft called Europa Clipper. There is no one on board. It is a robotic laboratory equipped with cameras, ice-penetrating radar, a magnetometer, and instruments designed to study Europa's surface, composition, and surrounding environment. Launched in October 2024, the spacecraft is already on its way and is expected to reach Jupiter in April 2030. It will not land on Europa, and it will not drill through the ice. Instead, while orbiting Jupiter, it is planned to make 49 close flybys of the Moon. Its instruments will investigate the nature of Europa's ice shell, search for evidence about the ocean beneath it, and study the Moon's composition and geology. Its purpose is not to detect life itself, but to answer a more fundamental question: does Europa possess the conditions that could support life? The answer may be no. Science makes no promises of discovery in advance. But the question itself became more compelling because of what we have learned from Earth's own ocean. Where scientists once expected the deep ocean to be nearly barren, exploration revealed thriving communities. Where life seemed impossible without the sun, Organisms were found living on chemical energy. Where the seabed appeared to be an endless, featureless plain, ancient geological records came into view. Formations that may take 1,000,000 years to grow by only a few millimeters. In the summer of 2026, remotely operated vehicles continue to move across the floor of the Pacific. Within the narrow beams of their lights, only a small fragment of this vast world appears at a time. A sponge, a sea lily, a translucent jellyfish, or a dark nodule whose growth may have begun millions of years ago. Beyond that beam, the darkness begins again. And perhaps the most remarkable thing of all is this. To search for the unknown, humanity does not always need to leave the Earth. Sometimes, it is enough to descend a few kilometers down.